Okay, I thought it'd be good to do one more problem on direction fields. Say we take 12 on page 8 and we get the initial differential equation that you see here. Now, I've already drawn the field because that takes a while to do, but let me show you how I would look at this and then come up with this. All we're saying is that the slope of the solution curve varies with apparently only y. Apparently, the slope of the solution curve only depends on y. All right? So, as I have said in other videos, there's some solution to this, and it takes the form y being a function of t, which we suppose we don't know, and it's over here somewhere, and its slope varies by that. Now, how do I look at this and give you that? Well, I noticed that if that's dy dt, it will be 0 if y is 0 or 5. So notice here at 0 on the y-axis, I've got horizontal lines all the way across, no matter what t is, because the slope of the solution curve only appears to depend on y. Same thing at 5, it's flat. No matter where the curve that's the solution to this thing is imposed on the yt plane, it must be horizontal at the position y is equal to 5. About the rest of it, well, I guess all that says is that the slope of the solution curve varies as a quadratic in y. So if we summarize this a little bit, we might draw a chart here and say, here's y, here's dy dt. At 5 and 0 for y, it's obvious that we get 0 for dy dt. But, doing a little sampling and thinking of this as being a quadratic that would have that shape to it, it would be at its minimum in the middle and positive on the edges. And you can try some sample points if you want to, outside of and in between 0 and 5, and that's what you're going to come up with. Now, how does it change from being positive to 0 to minus? It will change gradually. The slope will be positive, but as y tends towards 0, it will become smaller and smaller until it is 0. And then as the slope dy dt changes to negative, it will be gradual. And I suppose right in the middle, there will be some most negative slope that this thing's going to have. So, alright, so look over here real quick. Between 0 and 5, I have this gradual trend. The slope is 0, it's slightly negative, it's more negative. In the middle somewhere, it's the most negative it's going to be, and then it tends back to 0, okay? And from there, above 5 or below 0, the slope becomes more and more positive the further you get away in either direction from 0 or 5. So I look at this, and here's the direction field. Whatever the solution is to that, and there are many particular solutions all depending on initial conditions, it's got to impose itself over here and abide by the field lines. Okay? Because all this differential equation appears to do is describe the slope of the solution curve. If you read it just the way it is, that's what it says. Alright, now there were a few other questions about 12, and so here goes. Let's look at this one. What's the equilibrium solution? So what do we mean by equilibrium? That would be a solution that takes the form y being a function of t, of course, but that is constant. In other words, it doesn't vary with t. It's always the same no matter what t is. Can you pick out that equilibrium solution by looking at this? What kind of curve that we could impose on this direction field would always be the same? Imagine that you happen to be there. The slope is 0, the curve is flat, so that means you travel horizontally, but it's still 0. You have no way to escape. If you ever found yourself there on the solution curve, you'd have to stay there. It would be constant. Same thing with here. I'd take it y is equal to 5 and y is equal to 0. Those are the equilibrium solutions. But I guess another way we could figure that out is if we know that's the form it takes, we can make this operate in the original differential equation and then figure out what the constant has to be. So think of it like this. What's dy dt if y is a constant? It's 0. And then if y is a constant, there's your y and your 5 minus y. So let's do this. Let's say we want to find the equilibrium by this assumption of its form, and by that being the differential equation we're trying to solve. Just by mere substitution, we'll get 0 is equal to negative c times 5 minus c. And you want to know what c is to solve that equation. It has to be 0 or 5. So there's two equilibrium solutions. Y is equal to 0 or y is equal to 5. Now I don't want to make that look like I'm giving you an algebraic numerical solution. The solution that has to be a function. All right, these are just constant. So both of these are seen in light of this or that to be functions of t. All right, so there are the two equilibrium solutions. Now, let's say we want some extreme or long-term behavior to the solution curve. So investigate the behavior of the solution curve if t goes to infinity and the initial condition is y of 0 is k is some other constant. Well, I guess what happens as t goes to infinity, what happens to y, depends on where on the field you find yourself. Okay, so let's do this. I guess we're gonna have to answer this one in cases. Okay, so my first case, suppose that the initial condition was y of 0 was k, but k was greater than 5. Okay, so that would mean that there's some particular solution that abides by this field and has that point on it, which I suppose would be up there somewhere. So imagine there's this curve, it's got this point, it has positive slope right there. And as I travel along that curve, which has positive slope, I go over and up by that slope. I'm at some new point, and the slope is still positive. I have no way to get off of that curve that's rising if this point happens to be known on it. Okay, so you're there, and you're doing this. So it'd have to be that y goes to infinity. Okay? You send t to infinity. Based on the curve having that initial condition, this is what's going to happen to y. Okay, so the other case, suppose that, I guess if k was less than 5 at all, if k was between 0 and 5 or just less than 0. So let's say, what if k is less than 5? What if you found yourself at some initial condition that put you there? You would be on some curve that had negative slope at that point. You'd go over and down by that slope. You'd find yourself at a different point on the curve. The slope would still be negative. You go over and down. So you're trapped. And it appears to level out asymptotically to there. So if you're here, y is going to get pushed to 0 as t goes to infinity. Okay, but what if you were here? Same thing. You're on the solution curve. It has positive slope there. You go over and up, it still has positive slope. Over and up, there's no way to escape that. It's going to push you up again to 0. Okay? So, in that case, y will go to 0. Right, there's your long-term behavior as t goes to infinity if that's the nature of your initial condition. Now, I guess some fine print. For me to say that the initial condition puts me at some number less than 5, I didn't discuss what if it puts you at 0, okay? But still, if you're at 0, then, you're here, the curve is flat, you travel horizontally, it's still flat, you're stuck there. You have no way to get off if that's where you are and it's horizontal as you go over, okay? So y would go to 0 no matter what. Okay, so we got k greater than 5, k less than 5. What if k was 5? I guess that's the last case. Well, so if your initial condition puts you there, then as I mentioned, you're stuck. The curve you're on right there is horizontal, so you go over and it's still horizontal, so you're stuck there. Y would go to 5. So there's your long-term behavior as t goes to infinity. Well, it all depends on the nature of the initial condition. But I see all these just by thinking about what the curve would have to be like if it abides by this field and has the initial condition that's given.